two cycles, okay, which are permutations of the two objects, okay. Now, why do we worry about that, or why do we single that out as a nice way to represent it? Well, it's certainly not nice in the sense that the expression is products of disjoint cycles was. That is particularly nice. You really see the structure of what's going on. When you decompose any permutation, such as one like this here, into a product of transpositions, they are no longer disjoint. So you're doing one function on the 2 and 5 here, and then you're doing a function on the 2. So it is complicated. It's not easy to see the disjoint cycle structure when you're just looking at a long product of transpositions. But it is interesting just for the very fact that the number of transpositions required for any given permutation, such as this one on the left, is, well, not that the number is fixed, but that the parity of the number is fixed. So for any permutation that you start off with, when you decompose it into a product of transpositions, the number of transpositions that you see is either odd or even. So straight away you get this natural classification of all permutations in a given symmetric group into two kinds, as the odd ones and the even ones. So the way, I mean, we can obtain these products of anything into transpositions by using this principle for decomposing a single cycle. So a single cycle like this, which cycles the elements A1 to A2, A2 to A3, and so on, AN back to A1, that is equal to this product of transpositions. So you first swap the first two, then swap A1 and A3, and so on, all the way to there. So when you apply that decomposition to each of the cycles in the disjoint cycle expression, you get a whole long list of transpositions. And we quickly talk through the proof that the parity of the number of transpositions was always the same, so it's either always odd or always even. We proved that with a nice lemma. First of all, we proved the identity always had to be represented by an even number of transpositions. We did that by using an induction argument on the number of transpositions in the product. And then once you have that lemma, you can fairly easily then get the fact that any permutation, this is theorem 5.15 here, any permutation sigma, although it might be represented as a product of a different number of transpositions, they do have to have the same parity. If they don't have the same parity, then by taking one set over to the other side, you'll get an expression for the identity as an odd number of transpositions. If the amount of these here is odd and the amount of those is even, when you put the two lists together back to back, because by taking the inverses over the other side, you'll then have an odd number of transpositions for the identity, which is, of course, the contradiction of the previous lemma. So then this so this seems very natural, the way that if you look at any particular symmetric group, the permutations, they're all, each permutation is either odd or even. So it's a very natural splitting of the elements. Now, the identity is an even one. That's what the lemma said. The identity always requires an even number of transpositions. So that singles out, it's interesting to look at the set of all even permutations, and that's what's called the alternating group. So this is a very interesting subgroup of the symmetric group Sn. Okay, it's called the alternating. It consists of every permutation which is even. Okay, it's fairly straightforward proof that it's a subgroup. It contains the identity, because the identity is even. It's closed. So if you multiply two permutations, you just stick together their two representations as an even number of transpositions. So you've got an even number of transpositions. And to take the inverse of a product of transpositions, you just take the product of the same transpositions, but in the opposite order. Okay. Remember, each individual transposition is a self-inverse element. Okay. So the inverse of the big long product would just be the product of the inverses, but in the opposite order. So if there's an even number here, there has to be an even number here. It's the same ones, just put there in a different order. Okay. That gives us this very nice subgroup, and it has its size is half the size of Sn. Okay, and it comes up in a number of interesting areas. Okay, so it's an important class of subgroups that are always around. So that's more or less where we got to last time. We'll have a look shortly at some of the exercises when we're working with this cycle notation. But just to say a few words on dihedral groups. He's presenting them here as examples of permutation groups, and they are. But you can also speak about dihedral groups without specifically mentioning their representations as permutation groups. So the dihedral group Dn is the group of symmetries of the regular n-gon. So Dn. It's the symmetry group, the group of symmetries, the regular n-sided polygon. The regular polygons are, of course, the isosceles triangle, square, the pentagon, the regular pentagon there, the hexagon. So get the idea. These are all the regular n-sided polygons. So so the regular means all side lengths are the same, all the interior angles are the same. So they're the completely symmetric version of that n-sided thing. And these have interesting symmetries. They all have rotational symmetries. Okay? And it's not too hard to see that the basic rotation for each of them, well, the basic rotation for the triangle is a rotation of order 3, 1/3 of a full turn. The basic rotation for the square is a 1/4 of a full turn. 1/5 of a full turn for the pentagon and so on. Okay? So each one has a kind of fundamental rotational symmetry of, well, the n-sided polygon will be 1/n of a full turn. Okay? And by repeating that rotation, you can generate all the other rotations that that n-sided polygon has as symmetries. So those are the rotational symmetries. The reflectional symmetries, so the n-sided polygon, this is for that fact about the rotations, has n rotational symmetries. Now when I say it has n rotational symmetries, I'm including the identity as one of those. The identity kind of qualifies as a rotational symmetry. It's a rotation by a zero angle. R, basic rotation, r squared, r cubed, etc., all the way up as far as r to the n minus 1. So this is where r is, well, we normally have it as anti-clockwise rotation, although he might follow a different convention, but anti-clockwise rotation by 2 pi over n radians. Okay, just to be very specific. So those are rotational symmetries, but those are only half the total number of symmetries. These shapes also have reflectional symmetries. Okay? And the axes of reflectional symmetry kind of come in 2 flavors. For the odd-sided polygons, like the triangle and the pentagon, and the one after it, the heptagon, is 7-sided, is called heptagon. So these, I missed one for the pentagon. These axes of reflectional symmetry always go through one of the vertices and the midpoint of the opposite edge. Whereas for the even-sided ones, they're slightly different. There's 2 kinds of reflectional symmetry axes. There's ones joining the midpoints of opposite edges, and then there's another set joining opposite vertices. Okay? The midpoints of opposite edges, there'll be 3 of those for the hexagon, and then another 3 which are joining opposite vertices. Okay? To join your regular pentagon nicely, these are all intersecting in that single point in the center of the center of the polygon. So, and it's got, let's say, and reflection symmetries. Well, if we're still talking about the n-sided one, it'll have sigma 1, sigma 2, all the way up as far as sigma n. So you've got n of these reflectional axes of symmetry. So you see, the group consists of all these things. So the order of the group is 2 times n. So D3, the order of D3 is 6. There's 3 rotations and 3 reflections. The order of D4 is 8. Some books even, because of this, what's going on here with these indexes, some books will refer to the symmetry group of the triangle as D6, and the symmetry group of the square is D8. That's less common, I think, than using, so there they're using the index for the size of the group. I think it's more common to see the index being used for the number of sides of the polygon. Just if you are reading other sources, just be aware of that. If things look funny, it might be because they're using a slightly different convention about what the indexes represent. Now, what it's very nice to know about the dihedral groups is there's a very nice way of representing the elements. We don't actually need all these different symbols. Actually, we can simplify the notation. Well, we've already simplified it a little bit by just using one symbol really for the rotation, r, and then talking about r squared, r cubed, and so on. We don't actually need n separate symbols for the reflections, so we can simplify the notation by using. I think I might switch to s. I think he uses s in the by using s to denote one of the reflections. Then all the reflections can be represented as s, r after s, r squared after s, r cubed after s, etc., all the way up as far as r to the n minus 1 after s. So if we just signify one of these reflectional axes as being our basic reference one, and it doesn't matter which one, it's just purely arbitrary choice. You choose one of these as your single reference axis of symmetry, then all of the other ones can be all of the other reflection symmetries can be represented by composing one of the rotations after that reflection. You can see this, so let's see this in a non-trivial way. Let's look at the pentagon. So the pentagon, let's label the sides A, B, C, D, E. So let's suppose that that vertical axis is our reference reflection axis. Okay, so the symmetry S is to reflect the pentagon in that vertical axis. It will always draw a point, one of the vertices on the vertical line, and so that's S. If we did r squared after S, so let's perform S. So when we perform that reflection, still the same pentagon, but the labels have been swapped around slightly. So that's what you get by performing S. A is still fixed where it was, because that was on the reflection axis. And let's say then we do r squared. So r is rotation by 1/5 of a turn anti-clockwise. When we do r squared, it's moving everything on 2 positions. So it will go A, B, C, D, E. So that's the composition R squared after S. Now, if we just look at it as a one-step symmetry, what symmetry has been applied there from the beginning to the end? Well, it's a composition of a reflection and a rotation. So that has to be another kind of reflection. Because when you reflect things, it turns left-handed stuff into right-handed stuff. And then rotation keeps it as right-handed stuff. So overall, you've flipped you flipped the chirality of the stuff. You flipped the handedness. So you flipped it when you reflected, and then you rotated, which preserved the handedness. So it must be one of the reflections. You can detect what reflection it is by looking for which of the vertices has remained in the same position. E has remained in the same position, and A and D have swapped, and B and C have swapped. So really what we've done is we've just performed the reflection through that axis there. That was sigma, i.e. R squared after S is equal to the reflection of the axis. And by using the other rotations, R, R cubed, R4, etc., you can generate each of the other reflectional axes of symmetry. Okay. So if you like, so R squared has managed to move the symmetry axis kind of it's rotated around one click to the left. Yeah. If you look at all the other compositions, you can kind of pick up the pattern. But it's the kind of key factor to remember is that as long as you have the basic rotation and one of the reflections, by performing compositions of those, you can obtain all the other reflectional symmetries. Another key relation to know. That term relation is a kind of technical term. We'll see that occurring later on when we look at group presentations. And this is true in general. If you compose S after R, that's always going to be the same as R inverse after S. Now this is true in these dihedral groups, but it's true in a much more general setting. So this is true for any rotation R of the plane R2 about the origin, well, really about any fixed point, but let's just say the origin. It's true for any rotation R of R squared about the origin and a reflection S. So when you reflect the plane, you're reflecting it in an axis through the origin. So as long as you're talking about rotating around some fixed point, we'll say the origin, but just doesn't have to be the origin. As long as you're rotating around some fixed point, and S is a reflection in some axis of symmetry through that same point, when you compose S after R, that's always going to be the same as R inverse after S. You get the idea. If you first rotate it anti-clockwise and then reflect in that axis, remember, reflection takes left-handed stuff into right-handed stuff. So what the movement that was anti-clockwise, when it gets reflected, it turns into a movement clockwise. Yeah, that's the nature of reflections, what they do. So you can recover the same effect by first performing the reflection in that axis and then rotating everything. But you don't rotate it anti-clockwise, you rotate it clockwise by the same angle. And that's R inverse. Remember, if R is rotation anti-clockwise, R inverse will be rotation clockwise. R inverse will be that rotation. So these are kind of useful facts to know about these dihedral groups. Any questions about that? Now, in that way I presented them, I've stressed that the nature of the elements are transformations of the plane. But the viewpoint adopted in the book, and it does make sense in light of the way groups are represented in SAGE, and because of a theorem we're going to discover soon called Cayley's theorem. Really, every group can be represented as a group of permutations. There's a very, very natural way to represent dihedral groups as permutations. So by using a vertex labeling, I'll stick with D5 as my main example. That's what we were looking at there. By using a vertex labeling, or you can also use an edge labeling as well. I think vertex labelings are used most commonly, seems to be the tradition. So by using a vertex labeling of the polygon, Dn can be represented as a permutation group. So in other words, as a subgroup of Sn. Sn, remember, is the symmetric group on n letters, the group of all permutations of n objects. If we're using labels to label our vertices, that's n different objects, and each symmetry of the shape moves the vertex labels around somewhat. So they're all permutations of the n labels. So let's quickly, D5 isn't too complicated, there's only 10 elements. So can we really quickly draw 10 pentagons out of the question? If I'd been prepared, I'd have a lovely printed sheet with nice regular pentagons. 1, 2, 3, 4, 5. Let's do that. Okay, I've started now, so I might as well finish. 1, 2, 3, 4, 5, 6, 2 more. Okay, some of these are highly non-regular, but the important thing is to see what's happening with the labels, okay? So we're going to, okay, what are we actually going to do here? What we're going to do is, okay, we'll let these ones down the left be the images, the pentagon after we perform a certain symmetry. So over here on the right, maybe it's a bit perverse, I should have drawn it starting on the left, but ending on the right. So here's this, here we think that this is the starting off pentagon. It's got 5 vertex labels. And we'll apply each of the 10 symmetries that it has, and then we'll be able to read off the permutation representation of that symmetry. So, well, the simplest symmetry is the identity, the one that doesn't do anything to the pentagon at all. Okay. So you've got the identity. Normally that's just represented by E, or if you really have to give it a cycle symbol, you could just represent it as the simplest trivial cycle that you can, just the cycle consisting of 1. That sends 1 to 1, and by convention, the other symbols which aren't mentioned, it leaves them fixed as well. But then look at the rotation by 1/5 of a turn anti-clockwise. So you see there, what was at position 1, T5 is now appearing there. So 1 is being sent to 5. What was at position 2, sorry, what, yeah, the 1 is being sent to position 5. Sorry, I didn't do that right there. No, I put them in the wrong order. So I'm going to, sorry, the labels go around clockwise. So I rotate it 1 turn. Sorry, I'm just complicating things. Yeah, so if I rotate it 1 turn anti-clockwise, that's what it looks like. So 1 has been sent to the position that 5 previously held. 1 has been sent to 5. And 5 has been sent to the position previously held by 4. 4 has been sent to the position previously held by 3. You get the idea. 3 has been sent to the position previously held by 2, and so on. R squared, if you think about rotating it 2 clicks on, the labels are going to end up like this: 1, 2, 3, 4, 5. So R squared would be represented as so 1 gets sent to position 4, 2 gets sent to position, 4 will get sent to position over here, which was the position previously held by 2. 2 gets sent to position here, which is position 5, and 5 gets rotated over to there, which is position 3. Okay, so you can keep going like this, and you can look at R cubed and R4. Let's look at some of the reflections, just to get a feeling for what permutations they look like. If you reflect it in this axis, so call this S1, so reflecting it in that vertical axis will keep vertex 1 at the position it was. It'll swap 2 and 5 and swap 3 and 4. So that has kind of more different type of cycle symbol. That's the product of those two transpositions, 2, 5, and 3, 4. And you see all the other reflectional symmetries are going to be like this. If you look at S2, let's say S2 is this one. Reflection of this axis, that leaves 2 fixed, and then it's going to swap the other ones. Pairs, so 1 and 3 are going to swap, and 5 and 4 are going to swap. Okay. And S3 leaves 3 fixed, and it swaps positions 4 and 2, and 5 and 1. S4, you get the idea, it leaves 4 fixed, and it swaps 5 and 3, 2 and 1. And then S5 leaves 5 fixed and swaps positions 4 and 1 and 3 and 2. So I skipped over R3 and R4 just to save time. That kind of shows you how there's a very natural way to associate to each of these symmetries a permutation of n labels. And we know the symmetry group is a group, so then we now have a collection of permutations, which is a subgroup of Sn. Okay? Subgroup of size 2n. Does that get any questions off that? Okay, so there's some good material in that section there in the book. He goes through an example of a square rather than the pentagon, an example of 5.24, and shows you how each symmetry of the square is represented as a permutation of 4 symbols there. And he also looks at a 3-dimensional case. So a 3-dimensional case, he's looking at a cube, so a 3-dimensional figure. And the symmetry group he's looking at there is called the motion group. So that's only the group of rotational symmetries of the square. When people consider these 3-dimensional objects, they tend, or it's often the case that they focus on just the group of rotational symmetries, because those are the only ones we can actually achieve in reality. If you've got a 3-dimensional object, I can rotate it in any ways, but I can't actually reflect it. I can't actually turn my hand into a left-handed hand. I can kind of simulate it by flipping around like that, but I can't actually force my hand to turn into that one. They're just different. You can't physically achieve reflections. But I can rotate it in any kind of way. So rotations are the only kind of naturally occurring transformations in our space. So for that reason, we tend to only be interested in the rotational symmetries of a three-dimensional object. Often that's the case. And so in that example there on page 90, he's looking at cube and examining what rotations there. And you'll see, for instance, this labeling doesn't always have to be a vertex labeling. So when he's investigating, so again, the rotations of a three-dimensional object can be represented as permutations. But he's not doing, now it looks like he's labeling the vertices there, but he's only using labels 1 to 4. Cube has 8 vertices. The things he's labeling there are the diagonals. This diagonal from vertex 1 up here to vertex 1 down there, that's one of the diagonals of the cube. The cube has 4 diagonals. And so any rotational symmetry of the cube, you can record its effect just by noting what it does to the diagonals. It will permute the diagonals around in some way each time we do a different rotation of the cube. Now he proves here, there's a nice interesting argument here, which you can read through, that you can actually achieve any possible permutation of those 4 diagonals. So the symmetry group of the cube actually corresponds to the full symmetric group S4. The reason he shows that, the way he shows that you can achieve any possible permutation is he shows that you can achieve all of the individual transpositions. So there is a rotation of the cube that swaps diagonals 1 and 2 and preserves diagonals 3 and 4 in the same positions. And you can do that for every pair of the 4 diagonals. So if you can achieve all the transpositions by doing various compositions, you can then achieve any permutation whatsoever. Okay? Because remember, every permutation can be written as a composition of transpositions. So there's 24 different rotations of the cube. Because there's 24 elements in S4. Okay. Okay, so that kind of brings us to the exercises. We'll look at the SAGE exercises this evening in the lab session. Is everybody going to be there for the lab session tonight? Yeah. Okay. So is there any particular exercises at the end of chapter 5 that you've been looking at, or ones you wanted to specifically discuss? Okay, well, we could just start looking at a few of them and picking them up. The first few are all about working with the various permutation notations. So maybe one way to do exercise that maybe recaps a few of these things is, say, look at question 3C. Question 3C, the instruction is, so take this permutation 1426, 142, and express it as a product of transpositions and identify them as even or odd. Well, we could do this in a few different ways. We could either just take it, see, at the moment it's expressed as a product of cycles which are not disjoint. So we could just straight away decompose each of these individually into products of transpositions. We then have quite a long product of transpositions, and we could just count the number of them and see whether they are even or odd. So we'll do it that way. Another way is to first obtain its representation as a product of disjoint cycles. That's slightly more interesting. We can see slightly better what's going on with the permutation. So we'll do that afterwards. So first of all, we use the way that any cycle decomposes into products of transpositions. So that result is there on page 85. So this one, 1426. So first of all, we swap. So on the left, although strictly speaking, the first thing we're doing is we're swapping the labels in positions 1 and 2. within the transposition 1, 4, and then 1, 3, so then 1, 2, and then 1, 6. So that's the way that 1, 4, 2, 6 decomposes as a product of those, and then 1, 4, 2 will decompose as 1, 2, 1, 4, 4, 1, 2. Okay, so we see 5 transpositions there. 5 transpositions. None of them are just, they all involve 1, funnily enough. So none of them are disjoint, so we can't just trivially commute any of them. So there's no kind of really quick, trivial simplification of it. But it is an order 5, or it is 5 transpositions, so it's an odd permutation, so we certainly not the identity. The identity is always represented as a product of an even number. So it's an odd permutation. But we might also obtain it as a product of disjoint cycles. So to obtain it as a product of disjoint cycles, you might remember we did this in first year a bit. Well, one of the disjoint, well, you can either map out that diagram, you can either put all the symbols 1, 4, 2, and 6 just floating on the page, draw the arrows between them, and discover what the cycles are. We can do it a bit quicker. You can kind of do it in your head. One of the cycles is going to contain the number 1. So what comes after 1? Well, you just look at the total effect of the permutation on 1. The first cycle sends 1 to 4. Second cycle, because we're composing it, the second cycle sends 4 on to 2. Okay? So in total, 1 gets sent to 2. The first one sends 1 to 4, and that intermediate value is passed on to the second function in the composition, and that sends 4 to 2. So 1 gets sent to 2 by the permutation. You then look at what happens to 2, because that will be the continuation of this cycle. The first permutation sends 2 to 1, and the second one does something to 1, then it sends 1 to 4. So overall, 2 gets sent to 4. And then what happens to 4? 4 gets sent to 2, 2 gets sent to 6, so 4 gets sent to 6. And it's going to close now. The first one doesn't mention 6. This is where it's important, where we need this convention that we talked about, Jonathan, at the start. So the first one doesn't mention 6. So the first one leaves 6 fixed. And then the second one, since 6 is the intermediate value that's passed on, sends 6 to 1. So overall, 6 gets sent to 1. So you can see that that's back to the beginning of the cycle. So actually, what wasn't apparent from looking at either of these representations was actually this permutation is quite a simple cycle structure. It's just a single cycle sending the labels round one to the other in that order. Okay? That's really, I think, the usefulness of obtaining these things as products of disjoint cycles. You really see the fundamental nature of the permutation from it. Okay. Well, we're really only scratching the surface a little bit with these exercises, because there's loads of them there. But do any of the other ones leap out at you? And we might do another little bit of next week's lecture, maybe in some of these exercises, or maybe next Friday's one. There's lots of good ones here. Here's an interesting one. Question 8. Question 8 says, show that A10 show that A10 contains an element of order 15. Right. A10 contain an element of order 15. So i.e., we're looking for, i.e., does there exist sigma in A10? Sigma has to be even. Well, if it's in A10, it has to be even. So it's a product of an even number of transpositions. And is of order 15, so sigma 50 to the power of 15 should be the identity, and sigma n not equal to the identity for every n between 1 and 14. So 15 is the first time you see a power of sigma being equal to the identity element. Okay, now, how the heck do you think about this? Well, what it's talking about is see, if we have, consider a product of disjoint cycles. We'll worry about the evenness in a moment. Product of disjoint cycles. Let's call them A, B. Remember, disjoint cycles commute. AB is equal to B after A. It doesn't matter which one you apply first, because they're both operating on different symbols, so they don't interfere with each other. So you can apply them in either order, so they commute. So we've got sigma equal to a product of disjoint cycles. Also, since they commute, if you raise sigma to power n, so it's a times b to the n, but because they commute, we can move all the a's together and all the b's together and say that that's simply a to the n times b to the n. Well, then you can start to see, we'll be able to figure out what the orders is. See, because if A is a cycle of order S, and B a cycle of order T, then there's a very nice way to answer the question that implies the order of sigma is. Now, if we want sigma to be the identity, if we want a power of sigma to be the identity, A and B are disjoint, so they're doing things to disjoint sets of symbols. So the only way you can have a product of disjoint cycles being equal to the identity is if they're actually both equal to the identity, because one can't be the inverse of the other, because they're acting on disjoint sets of symbols. So the only way that this product could be equal to the identity is if both of them were equal to the identity. But if A is order S, that means the only powers of A that are equal to the identity are multiples of S. And B has order T, so the only power of B that's equal to the identity is powers where it's a multiple of T. That tells us what the order of sigma is going to be. So this order n has to simultaneously be a multiple of S and a multiple of T, and it has to be the first one of those that occurs. That's otherwise known as three-letter function last year from number theory. Smallest number that's a common multiple of them both. The least common multiple number we talked about, which remember was this partner to the GCD. GCD was the greatest common divisor. The LCM was the least common multiple. So the order of sigma then is going to be the least common multiple of S and T. First power n that you arrive at, which is simultaneously a multiple of S and a multiple of T. If it is, then A to the n will be the identity, B to the n will be the identity. So we can get an element of Sn, we'll worry about whether it's in An in a second. An element of Sn of order 15 can be constructed by using disjoint cycles, two disjoint cycles of orders. Well, we want to choose their orders so that the least common multiple is 15. So I think 5 and 3 is going to be the only way. So by using disjoint cycles of orders 3 and 5. So I could take sigma be a cycle of order 5, and then I want to disjoint one of order 3, so 8, 9, 10. Okay, they're disjoint, so powers of sigma will just be powers of the first one times powers of the second one. First one has order 5, so you're cyclically permuting 5 objects. So the power of this one to give you the identity has to be a multiple of 5. Power of this one to give you the identity has to be a multiple of 3. First such power you arrive at is 15, which is a multiple of both. Then we can worry about, is this an odd permutation? Sorry, is this an even permutation? It was asked to be in A10. Well, what's going to happen when we decompose this into product of cycles? Well, each one, a cycle which is an odd length, that is an even element, okay? Because this one will be 8, 10, 8, 9, and this one becomes 5, 4, 3, 1, 2. So they're each even, so the product of them is going to be even. So you go 1, 2, 3, 4, 5, 6. So it's an even number. That implies sigma in A10, in the alternating A10. Okay, so as you can see, there's loads more exercises there for you to try. I'd encourage you to work through them. I'll look through them again and pick out some interesting ones that maybe we shouldn't let, that are particularly interesting to notice, and we can talk about and include those in the problem session next Friday. So next week on the schedule, we're moving on to Lagrange's theorem, actually. I believe cosets and Lagrange's theorem, which is chapter 6. That's very nice. So that's where we're doing our first kind of substantial piece of group theory and such. Just been looking at lots of examples. But we'll be proving Lagrange's theorem there. Lagrange's theorem is very interesting. It says that in any finite group, order of any subgroup is always a factor of the order of the containing group. So it places a great restriction on the possibilities for subgroups. In a group of order 12, it's only possible to see subgroups of orders 1, trivial group, orders 2, 3, 4, 6, and 12 itself. You can't have subgroups of the other orders, and only the divisors of the order that contain them. So we'll be able to prove that for all groups in our lecture next week. Okay. So I'll see you this evening in the lab, where we'll go through the exercise.